Hello everyone. Now we are going to learn Schrodinger equation. First we will be dealing with the time dependent form of a Schrodinger equation. As we are familiar with the basic formalism of quantum mechanics, it would be easy for us to analyze the time dependent and independent Schrodinger equations. Now, to talk more about Schrodinger equation is the fundamental equation of quantum mechanics. It is in the same sense that second law of motion is a fundamental equation of Newtonian mechanics. Or we can say it is the wave equation in the variable psi. If you remember, when we learn wave equation, we usually write a second order equation and the solution of it will give the wave amplitude, that is y. Yeah, if you want, I can write this equation instead of writing psi, I can write it using y. So if I write it, it will be y is equal to a e raised to I omega t minus x by v. So this is the wave amplitude obtained, or what we have learned from the wave equation of a wave propagating in the positive x direction. It could be along string. Okay, so yeah, if I say the wave in the case, specifically in the case of a wave that is produced in a string, that can be forward moving as well as backward moving according to how we produce it. So this represents a wave moving in the positive x direction. If you remember, there will be waves produced in the string and propagating in the positive x direction. So using that equation, instead of the wave amplitude or displacement y, displacement is actually the height of the wave. Okay, so the height of the wave is the displacement, and in the case of material particles, using the de Broglie concept what we have learned previous to this chapter, what we have to use is, instead of the displacement, something visible like this, like either a water wave or a wave produced in a string, or if we consider the waves produced on the surface of a water body, all those represents a wave amplitude, something that we can see, we can measure, we can observe it and measure the height of the wave, that is the wave amplitude. But in the case of de Broglie matter waves, as we have learned, wave function represents the probability amplitude of finding the material particle in space and time. So using that probability amplitude, we are rewriting the same equation for the wave amplitude. So this is just replaced, y is just replaced with the psi, so that it represents the wave representing the material particle or de Broglie matter waves. So when we, before going into the details, we will just modify this equation from the fundamental values. You know that omega is 2 pi nu and v is nu lambda. So applying it here, what you observe is you can take out 2 pi, so it will be a e raised to minus I 2 pi nu t minus x by lambda. And once more, using the equation for energy and multiplying and dividing with the 2 pi, you will have 2 pi h cut nu. So from there you will have nu is equal to E by 2 pi h cut. Also from the de Broglie wavelength, we have the equation h by p. Again multiplying and dividing with 2 pi, you have 2 pi h cut by p. Substitute the values of nu and lambda in the equation. So we will attain this one. So now wave probability amplitude or the wave function represents this equation, that is a e raised to minus I by h cut et minus px. So I'm going to name it equation 1. So equation, we can say that equation 1 represents a wave equivalent of an unrestricted particle of total energy E and momentum P. You can see energy E and momentum P here, which is moving in the positive x direction, just like the harmonic displacement wave freely moving along a stretched string that we have that we were talking in the beginning. Okay, so this is the expression we have now. Now we can also formulate an equation for wave function using the concept of a wave packet. So using the concept of wave packet, what we have is the wave function of a matter wave is confined to a small region of space and it forms the wave packet. So mathematically it is a superposition of an infinite number of plane waves with slightly different k values. So that is a concept given by de Broglie. So putting those ideas together, we can write an expression like this, because wave function should be the superposition of infinite number of waves using the wave packet concept. So our wave probability amplitude or wave function should be represented like this using the wave vector k. Again modifying that, we know that E is equal to h cut omega and p square, which is equal to p square by 2m, giving p h cut k, that means h cut square k square by 2m, equating it to h cut omega. Cancelling one h cut, you have omega is equal to h cut omega square by 2m. So we have another more equation for the probability amplitude. So we have these two are two different forms of the wave function. In one case we are just considering a wave corresponding to a material particle in general, and in the other equation we are going with the mathematical concept That is the idea of superposition of an infinite number of plane waves with slightly different k values. So now we have these two equations. Now in order to obtain Schrodinger equation, what we are going to do is we are going to differentiate either of these equations, either 2a or 2b. Once with respect to t and twice with respect to x. Twice with respect to space coordinate, and because it is in one dimension we will use differentiation with respect to x, and differentiating once with respect to time coordinate, and modifying we can obtain time dependent form of a Schrodinger equation. So first of all, I would like to go for the simplest one, that is using equation 2a. And for examinations you can use either of these concepts in order to obtain time dependent Schrodinger equation. So I'll go for this one first, using the differentiation of 2a. Okay, our equation is psi is equal to a e raised to minus I by h cut et minus px, taking dou psi by dou t is equal to a is a constant, then differential of exponential is exponential itself, and we have to consider differentiation of t. So the coefficients come out minus I by h cut into e exponential minus I by h cut et minus px. Okay, now differential with respect to dou psi by dou x is again constant a into we have to take out the coefficient of x, that is minus I by h cut into minus p. So you will have minus I by h cut into minus p e raised to minus I by h cut et minus px. Okay, sorry, here, and once more differentiate it once more, that is dou square psi by dou x square. That means you will have a constant twice, taking I by h cut, and so let us combine it together. So plus I by h cut and p, both minus becomes plus, so square e raised to minus I by h cut et minus px. So this is equal to, now what we are going to do is we are going to rearrange it. If we rearrange it from the first equation, we'll just multiply it with I h cut. So here we have to multiply it I h cut, here also I h cut. So h cut cancels and I square is minus 1, so minus 1 into minus 1 plus, and only what remains is e. So this is equal to yeah, E into A e raised to I by h cut, sorry, minus I by h cut et minus px. So this is equal to E into psi. Actually it is, this part is psi. So as you know, this part is psi itself, this one. So we can write it as E into psi. Here also we are going to do the same kind of modification. So if we rearrange it, taking minus h cut square, see I square is there, so we have a minus, and in the numerator denominator we have h cut square. So taking that to left hand side, you can write, maybe I'll write it here once more. This is equal to minus 1 by h cut square p square a e raised to minus I by h cut et minus px. So taking minus 1 by h cut square to the left hand side, you will have minus h cut square dou square psi by dou x square is equal to p square psi. Okay. Now we should go for our general equation, that is a total energy equation in classical mechanics. So E is equal to p square by 2m plus v of x comma t. If we are considering the case of a free particle, then we can definitely avoid it. So first let me multiply it with respect to wave function p square by 2m into psi plus v of x comma t into psi. And now we have values for E psi and p square psi. So substituting the values, you will obtain I h cut dou psi by dou t is equal to minus h cut square by 2m dou square psi by dou x square plus v psi. So this is the time dependent, I should call time dependent Schrodinger equation in one dimension. Now if we write the three-dimensional case of it, we have to just extend it from x to xyz. So I h cut dou psi by dou t is equal to minus h cut square by 2m dou square by dou x square, okay, dou square psi by dou y square plus dou square psi by dou z square plus v psi. So this is the time dependent Schrodinger equation in three dimensions. So this is what we have obtained using 2a. This is the equation obtained using 2a. We can find the same procedure and using 2b obtain time dependent Schrodinger equation. Okay, so before that we will analyze it once more. Suppose if we are talking about the free particle case, for free particle, if we are asked to derive free particle time dependent Schrodinger equation, what we have to do is there is no force acting, or the net force acting on the free particle will be 0. So for free particle we should avoid the potential energy. So if we avoid potential energy term, what we get is only the first term in this equation. So we can write the first term in 1 dimension, also in 3 dimensions. So that represents the time dependent Schrodinger equation in the case of a free particle in 1 dimension, and also if we remove v from this equation, it will be time dependent Schrodinger equation for free particle in the case of 3 dimensions. As I mentioned, if we use equation 2b, just now what we have used is equation 2a. If we use equation 2b, also we can find the same Schrodinger equation just by following the same procedure, by differentiating the wave function psi of x comma t once with respect to time coordinate and also twice with respect to space coordinates, and rearranging it. So I think I'll go for that. Okay, so our wave function is integral wave function psi of x comma t is equal to integral minus infinity to plus infinity a of k exponential I kx minus I omega of k into t into dk. So differentiate it. Dou psi by dou t is equal to similar kind of differentiation. So integral minus infinity to plus infinity a of k, taking constant of this one time coordinate, constant value is minus h cut square. Yeah, for omega we gave the value of yeah, I'll rewrite it. For omega, what we have done is substituted the value of minus h cut square by h cut k square by 2m. So I think I should rewrite it. So it is h cut k square by 2m. Okay. Now the coefficient is minus I h cut k square by 2m into differential of exponential is that one itself, I kx minus I h cut k square by 2m into t dk. Now differentiating with respect to x twice, the coefficient of x comes out twice, because we have done the same differentiation earlier, just a slight difference in equation. So differentiating dou square psi by dou x square is equal to integral minus infinity to plus infinity a of k. Coefficient of x is ik, so I have to write it twice because I am differentiating it twice with respect to x. E raised to I kx minus I h cut k square by 2m into t, into t dk. Now this is actually dou psi by dou t. Dou psi by dou t can be rearranged by taking I h cut minus I h cut by 2m outside. So I'll write it. This is equal to minus I h cut by 2m into integral a of k square exponential dk. And here in the case of dou square psi by dou x square, this is minus of, because we have I square here, so minus of integral k square ak e raised to I etc. dk. Okay, so if we just analyze it, you can see that this part is the same here. So what we have to do is just give the value of minus dou square psi by dou x square here. If we have differentiated twice with respect to x, so since we are talking about free particle case, we can just substitute it here. Otherwise, like what we have done, take general equation of total energy in classical mechanics and apply it there, finding the values. Okay, so here we have integral k square a e raised to I exponential values into dk is here. So what we have to do is, the value of this integral is actually minus dou square psi by dou x square. So give it here. So rewriting dou psi by dou t is equal to minus I h cut by 2m into what we have is minus dou square psi by dou x square. So multiplying I h cut, here also one I h cut is multiplied, minus and minus becomes plus. So this one is both the minus become plus, but there is an I square, so minus h cut square by 2m dou square psi by dou x square. So this is the time dependent Schrodinger equation using the de Broglie wave packet concept, and this is the case where we have no potential energy. That is the case of a time dependent Schrodinger equation in the case of a free particle. Now we can extend it also, extend it to 3 dimensions by just giving dou, instead of dou square by dou x square, we can give the operator del, so that it represents the 3-dimensional equation. So it is I h cut dou psi by dou t is equal to minus h cut square by 2m del square psi. This is the time dependent Schrodinger equation for a free particle in 3 dimensions. And if we incorporate the potential value as well, this becomes I h cut dou psi by dou t is equal to minus h cut square by 2m del square plus v into psi. That means we have to give the kinetic energy part as well as the potential energy part. So this is the time dependent Schrodinger equation in this is the generalized form of a time dependent Schrodinger equation when there is a potential also exists. So from here, just modifying it, we can identify the values of operators. This one I h cut dou by dou t can be identified as operator E, and also minus h cut square by 2m del square can be written as minus I h cut del into this one into minus I h cut del. So that turns out to be p square by 2m. So that is a kinetic energy part. So we can identify this one as the momentum operator. Minus I h cut del is the momentum operator. So this is how we identify the operator values. So this is how we are deriving Schrodinger equation time dependent case using 2a and 2b. 2a is just using the wave equation idea from classical mechanics, and 2b is the wave packet idea introduced by de Broglie. So we can find time dependent Schrodinger equation using both 2a and 2b. Also, this is the time dependent equation. So we have a time part as well as spatial part. So this one represents the time dependent equation. This can also be rewritten like giving the operator values and identifying this as a Hamiltonian operator. This is identified as Hamiltonian operator. So this is written as h psi is equal to E psi is equal to h psi. Both are operators. E and h are identified as operators. So this is the time dependent Schrodinger equation and its derivation. I cannot say the derivation. It is what we have done is just rearranging a few of the concepts and attaining the time dependent Schrodinger equation. As I have mentioned, Schrodinger equation is the basic equation, and we are not supposed to get derived it from somewhere, because it is the fundamental equation of quantum mechanics in the same sense that second law of motion is the fundamental equation of Newtonian mechanics.